Okay. First, some introduction. This talk is actually like one of in a series of many, which was inspired by a quote from Herb Suter like 10 years ago. So appropriate for an anniversary. Basically, he said that there are some interesting problems in C++, which can be solved by a clever and small piece of code. And this is actually quite important because it is something that you will be able to take away from a talk like this. Of course, you will see like some simplified examples and some, but basically this is like production code. I'm not joking. It's like 5 lines, but it's production ready. Anyway, just a highlight. This talk is like a collection of 3 problems, which can be solved by some, say, clever log-free algorithm. So let's start with an introduction. I assume you all know what is a linked list. But first, some routine things about log-free algorithms. What do they do? Basically, whenever you need a synchronization object, like a mutex, you have a piece of code which must not be executed concurrently by multiple threads. And you can ask the operating system basically to coordinate the thread. Usually you say, okay, I'm going to acquire the mutex, and the operating system will like be a sort of arbiter between the threads and say, okay, now you go, okay, you ended, now you go, and that's okay. But this has some overhead because the transition between your code and the operating system takes some time. And especially if the required to execute the code is short, you may want to consider different, let's say, objects. Okay, so very typically in log-free algorithms, you use atomic operations. So in atomic operations, basically, you don't transition to kernel mode. You do all the operations in your code, and the operations are like active retries. So this means try to write this number. Did you succeed? No, retry. Was the number modified by someone else while I was trying to change it? Okay, redo something and retry. This, of course, is a trade-off. So you waste some CPU time. But in general, when the contention is, say, not too much, overall, the time required is like much lower. When I say much lower, means we have a unit test in our code base. This unit test used to say synchronize an access to an unordered map using a standard mutex, and then we changed this with log-free primitives, and the test dropped by 10,000 times. Okay, so this is what I mean by insanely low overhead. So if there is like not too much contention on the same thing, these things are fast. And when I say fast, I mean really fast. Now, one of the biggest issues that you may encounter when doing log-free code is that this code is basically undebuggable. So it's it's like extremely hard. So, and especially sometimes you think you can optimize it and you say, oh, I know, I can write this, I can save a, you know, a write here and cache the value here. Everything crashes. So it is extremely hard to optimize this code. So what we will, small spoiler, what we will see in this talk is a very small piece of code, which is small enough that you can understand that it's correct. And you can reuse it really in a lot of places. Okay, but first some theory. In literature, we have some literature about linked, say, atomic linked lists. So, say, one of the first, not Jim Davis, but so one of the oldest references is Triber. This is often called the Triber algorithm. And it dates to 1986. Okay, so there was no C++ at the time. But he wrote an article saying, oh, we can, with the modern computers, we can write a lock-free linked list that works like this and this and this. Now, this original article cannot be, it can't work. As written, it doesn't work in C++ because their memory model was completely different at the time. But there is a very good point, which is we can, say, cut out the part of the code that doesn't work today. And we get something which is, you will see, very, very reusable. So this is a linked list. So the linked list is just the head, okay, a pointer to the head node. And this is the algorithm that does that pushes a node to the top of the list. So what does this code do? So I pass something, you know, some value of unspecified type, and the algorithm creates a new node, which is private. So no other thread can see this node named n. Very original. So what does this loop do? This loop says, point my new node to, so that the next is the original head, okay? And then try to write this node into the head of the list. Did I succeed? No, retry. In the meanwhile, the head of the list probably changed, but my pointer was updated too. So I can basically just retry, just set the next pointer and retry, okay? This is fantastic to get into the spirit of lock-free programming. The spirit of lock-free programming is, I create something which is aside. It's private. Okay, I have a node which is my own. No other thread can see it. Then when I'm ready, I atomically put it in place. From that point on, I don't have any more control of that node because anyone may see it and do it and read it, and there is no lock. Okay, so when I wrote my node into the head of the list, it is lost in some sense. I cannot delete it, for example, because someone may be reading it, like the very same instant. So a list that has only push front is a bit pointless. So I can do two things with a list. Why two? Because I don't want to do things that are like too expensive. So one of the things I may do is return the front element. Okay, this is easy and totally thread safe. the second thing that I can do is I can take over entirely the list. Okay, so I tear it away. Okay, I replace the list with a null. From that point on, the list is like private to me. Nobody can get it anymore. If someone else tries to get it, it will get a null pointer. When the list is mine, I can basically, well, not that I can, but let's see what I mean. When the list, after the list is my private property, I can iterate over it and destroy it. Okay? Is this safe? No, not both. One of the two. Okay? So if you have a list where you may return the first element to someone else, then you cannot delete anything. Okay? But sometimes you can, so basically you will construct, you can construct a list that has either push front and front, or push front and pop all. Not all of three at the same time. Okay? If you mix all of them, it's a recipe for disaster. And so let's be a bit pessimistic for the moment, and let's see why. As I anticipated, the point is that there is no lock whatsoever, right? So anyone may have a pointer to a node anytime, okay? Not to a node, but to an element that is inside a node. So so if another thread deletes the node, boom, okay? And there is no way they can coordinate. In fact, this list does not even have a destructor. Okay? It does new, but it does not delete by default. If you want to delete the elements, then you can call pop all and pass an empty callback. We will see it. But it doesn't do automatically. You have to guarantee yourself that you can do it. Side note, whenever you think you can add front, you can add also find if and visit. Basically, find if stops, so they basically iterate over the list. Find if stops at the first, and visit loops on everything. They have like the same degree of safety as first. We will see they will be useful later. But let's see the pessimistic part first. Suppose you have a thread. So this code is run in a thread, and the thread, your operating system decides to pose the thread here. Okay, you have a thread here. Then another thread comes, and the other thread is given some priority, and it arrives here. Okay, you see where I'm going. So front and pop all cannot mix, because there is no way you can know when a pointer is in use by someone else. Second example, Treiber, in his original article, he wrote a pop. Okay, so this is more or less the translation in C++ of his pop algorithm. The problem is, so you write it, you write a unit test, it works. Why not? Fantastic. The problem is that there is a delete here. So this function is doomed, because when you pop a node from the list, you try to delete it, and that's not a good idea. More precisely, suppose that two threads are doing a pop simultaneously. The first thread arrives here, and it tries to read the next pointer from the node, which is perfectly fine. It is paused by the operating system. Then another thread comes and goes straight to the end. And unfortunately, that node was deleted here. Okay, so so when you try to delete the next pointer, you are reading from deleted memory on defined behavior, and that's bad. So not that I was photographed when I was saying bad. Okay, so remember, bad. Another side note, you may know that atomics have these memory models. So you can try to optimize them by saying, oh, here, don't read with sequential consistency, read with release, semantics, acquire. So if you really know what you are doing, you may try. If you don't try. Because so even if you succeed, you will not get a lot of improvements. And there is a big risk because on Intel processors, these things work in a very different way. So you write the code, you test it, it works fantastically. You migrate to ARM, it crashes. Okay, you don't want to meet these things in production. In my company, we compile for 3 different operating systems and 2 different processors. So you don't want to put a bug that is visible only in one of the combinations, and maybe figure it out like the day before the release. That's why I said no. Maybe if you want to optimize, then it's a good idea to reduce the false sharing, which is I don't want to talk about it because it's a long story. There is a link here which you can read if you feel brave. That is a very good site about log-free programming anyway. The problem with reducing sharing is that it's sometimes not very usable in practice. So it's like a cache effect in the CPU. If you read 2 things that are too close, basically the CPU will think that they are part of the same cache line. And in fact, they are not. Maybe like one of the 2 things is modified often, and the other one, well, when you modify one of the 2, the CPU has to reread the entire cache line. So you generally may want to add some padding to have these things like very far one another. But this sometimes makes your objects too big. So you can't do it. Okay. But anyway, let's instead be a bit more optimistic. This the end of the pessimistic part. From now on, I will be like more, I will show you what you can do it, what you can do, not what you can't do it. So the problems. The first problem is called read often, write rarely. So these are the hypotheses of the problem. It's like pretty common. You have like a global variable. You read it like very often from multiple threads. And sometimes, but really sometimes you update it. You have an interface, you have 2 functions to read, set the variable, blah, blah. And you want to optimize this like to the extreme. What is the obvious naive solution? mutex. You write a global variable, you protect it with a global mutex, and you acquire the mutex before doing any operation. Okay, that's like the super basic level 0 thing. There are, so note that you have to return a copy of the variable, because you can do the copy under the lock, and you can't return a reference because the reference would escape the lock. So that would be bad. This is so sometimes this say when you propose a lock-free solution to a problem, you get like surprised faces and expressions, and the reason is that you sometimes have to you know, sometimes lock-free solutions are very different from the naive solutions. So, for example, you have to question things that superficially may look like very important. For example, what if I tell you, don't keep like one single value for the variable? Here we have like one global variable with one value. Okay, I tell you, okay, why do you keep just one? Keep many. So superficially, you may look at me like, he is crazy. Okay. Well, no. So this is exactly like the perfect case for an atomic linked list. With front. Okay, so I always want to read the front value from the list. So no lock, super fast. I read a pointer. What could be faster? If I change the value, I just push front a new value. What's the problem? I never delete the old one. But the hypothesis of the problem says precisely that the value is updated rarely. So who cares? If it's a string, the worst case, I keep around an allocated object until the end of the program. It's like, what could be? 100 bytes? Who cares? Maybe I read this like hundreds of times per second from multiple threads. So who cares if I waste 100 bytes until the end of the program? So this is like the full code of the solution. I write a wrapper for the atomic list that destroys the value at the end. And basically what I do is I push front when there is a new value, and I read the head when I'm asked to, and I can return a reference. So I also get the bonus point for returning the reference. Any question? Please.
I don't know if I'm getting right, but are you saying that basically the trade-off to have a faster programmer using this lock-free approach is that you can't avoid memory leaking, and if these kind of structures are within, for big chunk of data, memory saturation?
No. So yeah. So the question is, can you what to do if these things saturate the memory because you cannot delete anything from the list? Yeah. What I'm saying is that this is true. I mean, if the object was like 1 gigabyte, then you don't want to apply this strategy. Or alternatively, what you can do instead, you can add your own logic. Okay, so for example, maybe you know that in your application, maybe you know that in your application, after like 1 minute, you can delete the old objects. Okay, but this is not something that the atomic list will do for you. Okay, My point is the atomic list can delete all the objects, but it will not do it for you automatically because it does not know if it's safe to do it. You have to do it. Okay, in this case, this is like a global variable somewhere, this one. Okay, so being a global variable, say, let's pretend that it's safe to destroy. So it does it. Okay, but not in general. Problem number 2. Multiple producer, say multiple consumer, multiple producer, whatever. So the idea is you have an object that represents a task. Multiple threads post tasks to execute in a queue. And then you have like one or more executors, workers, whatever, call them as you prefer. The workers consume the items in the queue. One of my favorite examples is logging. Okay, a line in a log is a work item. Okay, I can post a tuple of integers, doubles, strings, whatever, and I want the worker thread to format the line, add the timestamp, maybe do some sorting, and then write to a file. Okay, why not? So the idea is that the thread that wants to log something has to do the minimal amount of work. So even like formatting the string is some work. So why don't you delegate to the other thread? This is a use case for the other version of the linked list. So with pop all. Let's say this is like some preliminary definitions. Let's say you have an active thread running. Let's say is every 2 seconds, pop the entire list. Take anything in the list, format the lines, sort, write to file. Sleep for 2 seconds. Okay, I'm simplifying a bit, but you got the idea. So logging is a push front. Okay, for simplicity, I'm posting a tuple of which is like partially pre-formatted, but you can add like whatever you want. You can make it more complicated. But the idea is logging is I add a tuple in a list, and then there is another thread that does the work. But you see, the code is like super minimal. There is a global variable that opens a log file, and there is a global function that returns the list, which is part of the structure. Let's see more precisely what I hid initially in the comment. Literally, this is all the code. Okay. It's simplified, whatever, but this is all the code. So that basically the thread does forever sleep and flash. And flash means pop all the things that are in the list, convert all of them to string, sort the strings, whatever, sort by timestamp, remove duplicates. You can, do whatever you want, and then write all of them to the file. Please.
This means that we have to elaborate all the items all together. What if we want to split the load among different threads?
So in the case of logging, you generally, from my experience, for logging, the best solution is to have one dedicated thread that does all the work. For example, if you want to, say, delete duplicate lines. I'm not sure if you have recently opened, say, Linux log file or macOS log file. Sometimes it says the previous log line was repeated 200 times. If you want to do this, basically processing log lines, you will see that it's more convenient to process all of them from a single thread rather than from multiple. But there is nothing that prevents you from doing a pop all simultaneously from multiple threads. Okay, so pop all is thread safe. If you do it like too often, say one of the threads will get something and others will get nothing maybe. But this approach is literally scalable. Not sure if I answered satisfactorily. Anyway, you can see, so this is the work that I was mentioning. So this thread does the formatting, and it does also the sorting. You can do, as I said, you can make it more complicated if you want. In our production code, for example, we do have deduplication, which is, if you want to add deduplication, you will see that the code is not that short, but it can be done precisely with this approach. The last problem. Here, let me start not from the, oops. Let me start not from the hypothesis, but from an example. Suppose you have a global map and you do lookups. Okay, this map is synchronized, blah, blah, so it's super slow. There are multiple threads that do lookups simultaneously, and this map like occasionally changes, but not that often. So the second step is, okay, let's add a cache. So every thread has a cache for lookups. So, and okay, this is the code for the local cache. So every thread has an unordered map, and it does a lookup trying the local cache first, and this trick is like super compact. There is a reason why this series of talks is like problems in 10 lines of code. Anyway, the problem is, how do I tell threads that it's time to clear their cache? Okay, you are with me. So every thread has its own map. And how can I tell them to clear it? It's like their private property. And here is a solution. There is obviously more than one, but this is the idea. So when a thread where a thread constructs its cache, I also construct an object which is a message. Allow me to use some weird terminology so to impress you and confuse you completely. So I have an object which is called notification hub. It's a global. It's basically like a global variable, and a global variable. So I can create a thread local message that receives messages that are put in this notification hub. Any thread says, if my message is true, clear the cache. Okay, so every thread individually reads its message. On the other side, there is another thread somewhere else that says hub broadcast the message through to everyone. Okay. Nice, isn't it? The hub is an atomic linked list. Okay. And so the only, say, conceptual difference is that the nodes in this list are reference counted. They have a reference count of 2, because one is the node inside the list, and one is the node, the local reference to the node owned by the thread, the message, okay, owned by the thread. Basically, the message is just like a pointer to one node of the list. This machinery is required because sometimes your threads will die before the hub. Sometimes the hub will die before the threads. Okay, so so you basically have nodes that have a reference count starting at 2, and then you decrease it when the hub is destroyed or where the thread is destroyed. Broadcast is simply visit the list and set everything to true, everything that you find to true. Okay. Sorry, it's a bit, the font is a bit small, but here you can, if you had like very good glasses, you can read ref count equal to 2. But more than the details of the code which you will find on the slides, I wanted to focus on how big the entire code is. Okay, so the entire code is like 40 lines. And it's 40 lines because I basically wrote some member functions with the names in this fake terminology. So to, I wrote a function that is called onMessages, which is basically just a wrapper for visit. Okay, so of these 40 lines, like 10 is boilerplate, just to make it a bit more user-friendly, but the point is where you see the problem that you can never remove anything from a linked list. You see it because the hub contains one object per thread. So when the thread is created, it does a push front in the hub. But when the thread dies, it never pops anything from the hub. Okay, so there is a node which is dead. Okay, so if your application creates like 1,000,000 threads and then destroys all of them, and then another 1,000,000 threads and then destroys them, this is not a good idea, because your hub will grow. Okay, but if you have a thread pool that contains 1,000,000 threads and that's all, okay, it's fantastic, because every thread has one message. There is no lookup, no, literally everything is like instant. It's constant time. When a thread wants to see if there is something to do, it is one atomic read. Okay, 0. You cannot be faster than this. Okay, not even in Rust. So if you are curious, this is like the full code. You see that the message is like a pointer to the node. Okay, literally. It is exactly the same thing rewritten with a different terminology. So literally nothing new. Say this is the same push front, which is slightly modified because I'm passing the pointer instead of doing the new from inside. But okay, it's literally the same code. This is visit. Okay. Same push front, same visit. Okay, time for the summary. You probably are familiar with the law of the instrument. If you have a hammer, then everything to you looks like a nail. If you have an atomic list, you will solve everything with a push front. If there are questions, it's a good time. Otherwise, I have a bonus slide.
Actually, I have a question.
Please.
Probably, since it's a different paradigm than what I'm used to work, one question that comes to my mind is, what if I want to update that?
You do a push front with a copy. So you take advantage of the fact that find the first, stop at the first. Right. Okay. So if you have, say, this is something that is actually explained in the bonus slide. So think like your value is a pair, is like key value. Okay. So assume that you want to do a scan in the list and say find the value associated to the to foo. Okay, to the value something. Find first will stop at the first match. This means that if you do a push front with the same key but a different value, you solve your problem. Because this is like super thread safe. So the threads that are already doing a find for the old value will find one. New threads will find the new one. This, in fact, is the basis for the atomic hash table. So with this machinery, you can do an atomic hash table, which is basically like an array of atomic lists. It requires to modify slightly. You see, you have to write push front taking the node which is allocated outside, but who cares? So this is an idea. This is exactly your question. When you want to erase, for example, you mark the node as erased and it will be skipped. We have an hash table in our code base, which is where the type T of this is a triplet hash key value. And the hash is an atomic. So when you want to erase something, you just set the hash to like an invalid value. Find checks if both the hash and the key match. So it will never find anything that was deleted. And if you want to do an update, you just push a new value to the front of the same bucket and it works. I can tell you that, so I spent some time writing a proper atomic hash table based on these things. And the code is 1,300 lines, roughly, which is not small, I mean. But the majority of the code is for this. Because, so think like you have an array of atomic lists and you want to create a bigger array and copy everything in the new array. It's a nightmare. You have no lock whatsoever. So like of these 1,300 lines, I would say probably half is just for the machinery required to do like let's call them expensive operations. But say basically, if you just need find, erase, insert with overwrite, you can do it like super easily. I think this is all the code. Okay, as usual. It's no other question.